again, just to show you the current architecture of the ExoMars, or the Joint Mars Exploration Program, trace gas orbiter, so looking for methane in more detail on Mars, but also acting as a data relay for the rovers in 2018. And again, in this audience, I don't want to go into that in great detail. LISA Pathfinder, again, is a demonstrator, technology demonstrator mission, essentially taking LISA, which is a 5 million kilometer baseline interferometer, and shrinking it down to a meter or two, and doing interferometry internally in LISA over those small scales to prove that you can actually have a drag-free system that is not influenced by the outside environment. So, of course, all of the free-floating masses, which you do the interferometry between in the vacuum chambers inside, and then the whole system inside, has to be kept drag-free in order to be able to measure this extremely high precision, the interferometry that you want to do. There's a whole lot of technologies being developed and being put together. The optical bench up here, the test masses here in the cryogenic chambers, linked by the optical bench in the middle, and then two drag-free systems, a FEEP from ESA and a colloidal thruster, which somebody described to me last week as a very expensive inkjet printer. Very small droplets of material which flow out in order to have very, very low thrust. So keep this whole satellite balanced from being buffeted by the environment that it's in. And then also it's being launched on a new rocket which we're developing in ESA, the Vega, and it'll be launched on the third launch of Vega, not the first one as we did with Cluster of Ariane 5, which wasn't a good choice. Then moving on to Gaia. Gaia is a high-precision astrometry mission, something like 100 times more accurate than its predecessor, Hipparcos. Will be surveying a huge volume of the galaxy, most of the Milky Way, doing a huge range of science. Of course, Hipparcos is known for measuring the positions of objects, but once you can measure the positions of objects to extremely high precision, you open up an enormous amount of scientific parameter space. So Gaia will discover tens of thousands of exoplanets by astrometry. It will do tests of general relativity. It will understand, give information to help understand the formation and evolution of our own galaxy by looking for moving groups and tidal streams. So Gaia is a very important project for us, and something which we are very much looking forward to launching at the end of 2012. To show you a bit of the progress, one of the things you need in a precision astrometry mission is an extremely stiff optical bench. And so this is a 3-meter diameter silicon carbide torus, which has been made by Boostech in Europe. And you can see all of the brazings and all the fittings to put all of the mirrors that then go on here. And one of the main components that needs to go on, of course, is the focal plane. And this is an engineering model of all of the CCDs here. As Gaia is spinning, the stars drift across the focal plane and are measured for as astrometric location, but also photometry and spectroscopy as well, as they drift across the focal plane here. And this has proven rather difficult to put together, and in particular to mitigate radiation damage on the CCDs, but we think we're out of the woods on that by now, and we understand the performance of Gaia will be fairly close to the specifications. There will be a talk by one of my colleagues from ESTEC on Gaia later in this meeting if you want more information there. JWST, well, again, you should have heard a lot about that in the last couple of days, in particular on Sunday with a large session there. Of course, this is a hugely exciting mission and a huge mission in many ways, and Europe is very pleased to be partnering with both NASA and the Canadian Space Agency on this. And of course, we're particularly happy that we have about half of the focal plane by having the MIRI instrument, which is a European consortium, plus NASA, NearSpec, which is coming from ESA, with contributions from Goddard, and also we're providing the launcher, the Ariane 5. And here you may have seen pictures in Stefan Berkman's talk earlier in the week. This is the engineering test unit of NearSpec. What's quite interesting about this is the ground-based telescopes evolved towards massive, huge instruments which they put on their various foci. These are actually almost classical-sized instruments. They're not terribly large, of course, and they can't be given the size and weight constraints, but very, very powerful, and a lot of technology built into this with the micro-shutter arrays and the integral field unit, which will be used here, so multi-object spectroscopy and integral field unit imaging. So look out for that. There's a lot of science across the whole of JWST's domain there. And the last of the missions which we're implementing today, and I won't say anything about it for you for this audience, but it's for our planetary colleagues, a very exciting mission to Mercury in collaboration with JAXA. BepiColombo, which involves a magnetospheric part here in the front, which is spinning, and then a fully 3-axis stabilized part, which is the polar orbiter, which goes over the poles of Mercury. And the launch date, if you can see just down the corner, 2015. So let's, in the last part, move on to our Cosmic Vision program. Now, Cosmic Vision is an aim to put some structure, if you like, bottom-up structure, if that makes sense, some idea of making sure that we keep a science-led program in ESA. Of course, everybody who's associated with the space agency knows how political these things can be. But it's very, very important to us that the space science program is a mandatory part of the ESA program. If you're a member of ESA, you have to contribute to the space science program. Many of the other programs we have, telecommunications, navigation, launches, and so on, are optional. But what it means for us is that we can try and keep a very strong bottom-up science-driven program. And so Cosmic Vision was put together to put some structure on the science program for this time frame, 2015-2025. And here are listed on the left-hand side are all the rather obvious things that you would want to do, from nearby universe science, planets, life, the solar system, looking out into the distant universe, looking at fundamental laws of gravity and dark energy and dark matter, as you'll see in a moment, and then looking at how the universe was put together in its early phases. So this book has provided a template for the community to then come back and propose missions against under the following framework. And that framework is that we're allocating over a 10-year period about 3 billion euros. So in 3 slices, Cosmic Vision 1, 2, and 3. This is how it was originally foreseen. It's turning out to be a little bit more micro-sliced, shall we say, at the moment, as you'll see in a little while. So 3 announcements of opportunities, 1 billion per time, but also, very importantly, partnerships with our internally with our member states providing payload on many of these missions, and then with our international partners. And almost all of our missions actually have very strong international partnerships. So we have L-class missions, which are seen to be observatory class or large-scale exploration, outer solar system in particular, and the ESA contribution to those is 650 million. Again, the ESA contribution. Many of these missions are a lot more expensive than that, but involve our international partners. And then the M-class missions, which have been running a little bit ahead of the game, are those which were originally set to be about 300 million, but it was seen during our Cosmic Vision 1 studies that these are running up to 450 million cost to ESA. So, of course, you'll say, well, that's encroaching on this somewhat. And we're beginning to think about whether these labels make a lot of sense. We shouldn't be perhaps so prescriptive. But the top-level envelope, of course, remains the same. So let me say a few words about the missions which we're currently studying. In fact, we're beyond the study phase for the M missions now. We're in a competitive definition phase, which is something that ESA hasn't done before. Typically, at the end of the study phase, we would pick one mission, then go do it, but you maybe don't understand it in enough detail at that point to be able to be sure that you're controlling the costs and the schedule. So the idea here is to have a lot more work done through the definition phase, but competitively, and then pick the winners out of that. So we have 3 M missions at the moment. Euclid is a dark universe mission, not only dark energy, but also dark matter, and it's a 1.2 meter telescope with a visible and infrared set of instruments in the back here, both imaging and spectroscopy in the near infrared, looking at evolving cosmic structure. So on one part, looking at lensing, weak lensing, looking for shear in objects seen from the far universe as their light traverses the universe towards us. It's gravitationally distorted by intervening lumps of dark matter. And to do that, we want to have high precision, high resolution, wide field visible imaging. And this is, of course, a challenge to get extremely stable focal planes in order to be able to measure this very small amount of distortion with near infrared imaging photometry to get redshifts, photo-Zs. And then the other probe which we're using is baryon acoustic oscillation, so using the scale size, the scale length of about 150 megaparsecs, which is imprinted from the CMB, and how that evolves as a standard ruler over time. And Roberto talked a little bit about this in his talk about how you use these standard rulers to determine this, the change in the acceleration of the universe as the universe is expanded. To get to the dark energy, and to do that we need much more accurate redshifts to create 3-dimensional maps, as you see represented in the simulation here. And so the aim of Euclid fundamentally is to do this over half the sky with this 1.2 meter telescope over a 5-year mission, and to get down to the well-known dark energy parameters. So W, the pressure to density ratio, down to 1%, and WA, the change in that with time, to about 10%. And I will say that at the moment we have on the table an offer to NASA to have a collaboration in this mission at about the 20% level. And of course, we're all very interested to see how that turns out from the decadal survey, which is ongoing here in the US. And there will be, of course, talks on both Euclid later in this week and also on the US side, JDEM, the equivalent mission here. Moving on to PLATO. PLATO is a mission to discover exoplanets. Both Evina and Roberto told you they're going to characterize exoplanets, but not necessarily look for them. PLATO is very definitely there to look for them, and it's to look for them in the nearby part of the galaxy by doing a very wide field survey rather than a narrower targeted survey that has been done by Kepler and Corot. Here's the Kepler field of view imprinted on the galaxy, and here are some of the Corot fields. PLATO is going to use very small cameras, but many of them, to look at much larger areas of the sky, and therefore typically discover much nearer objects. So the aim is to discover transiting exoplanets around stars which are close enough by to have much more accurate follow-up, both in terms of the radial velocity work, but also in terms of astroseismology, which PLATO will also do to characterize the stars much more accurately. So these are the two PLATO main fields as they currently look, just on the edge of the galactic plane, but also PLATO will have a phase at the end of its mission where it actually covers a very substantial area of the sky with shorter periods. We also have in competition here in this definition phase